You already know what the fuck is up. Do you know what fucking time it is? Yeah, it's the Carboniferous period. I've been stoked to start researching this one. And then I started researching it, and holy shit, reality slapped me in the face. As we've gone through these episodes, I'm sure it's been clear, and we all know that I kind of brush past the plant stuff. I'm not a botanist, so I give you the quick bullet points and then move on to what I'm comfortable with. The animals. But that was not possible with this episode, because really, the plants in this period are the star of the show. If you've ever heard of the Carboniferous, your main takeaway from it was probably that some of the insects were fucking massive, because there was a lot more oxygen in the atmosphere than there is today. 30% compared to today's 21%. That is because of the plants. And so, the last few weeks I have spent...
They ask you how you are, and you just...
a lot of time making sure I have a good grasp on the how and the why of that aspect. And God, I hope it makes sense when I explain it to you. So let's just get on with it. My name is Lindsay Nikole, and this is the history of life on Earth. That we know of. We're going to start off by getting the global conditions out of the way. So back in the Devonian, we had supercontinent Gondwana in the southern hemisphere, and then its buddy, supercontinent Euramerica, kind of situated at the equator, just above it. Well, in the Carboniferous, Gondwana was really cozying up and started moving closer and closer to LaRussia. Now you're probably thinking, wait, what the fuck happened to Euramerica? I was thinking the same thing. Who's this new LaRussia character? For this section, the continental tectonic shit section of this series, I tend to keep the sources pretty simple, like university pages like Berkeley, and all of them just switched it up. In the Devonian, they were talking about Gondwana and Euramerica, and then all of a sudden the Carboniferous was Gondwana and LaRussia. So I looked into it, and based on my understanding, it seems that Euramerica broke apart, and one of those new fragments was LaRussia. Necessary context? Probably not. You don't need to remember that, because at the very end of this period, all of the continents finally came together to form the one and only. You know it, you love it. Super motherfucking continent Pangea. So keep that in mind. Throughout the Carboniferous, the continents are getting nice and cozy until at the very ends they form Pangea. So once the next period comes about, the Permian period, Pangea is absolutely kicking. So while these land masses were kind of slowly moving in as the backdrop of this period, the global climate was shifting pretty significantly as well. The early Carboniferous period was real swampy. That's a mourning dove. I don't know if you can hear it in the microphone. The early Carboniferous was real swampy, wet and humid, tropical. Think of Florida on a larger scale, with creatures that seemed like Florida inhabitants as well, that I'll show you in a minute. And then as this period moved along, the climate generally got cooler and drier. Think more temperate, maybe? There were more climatic fluctuations due to glaciation at the poles. So the shift from warm and humid to cool and dry led to some pretty serious adaptations in many groups, including in our ancestors, that I will show you in a minute. You might have heard the Carboniferous period be referred to as the age of the insects, because insects and other related groups were going absolutely nuts during this time, with some getting to the biggest sizes the world has ever seen, that we know of. Before we get into why that happened, I want to tell you about today's very on-brand sponsor, the ants. Underground Kingdom. Get it? Because ants are insects. They weren't alive yet, but they're insects nonetheless. The Ants Underground Kingdom is a strategy mobile game that allows you to simulate the life of an ant colony, manage resource gathering, defense against predators, and more. You start off with a small colony and assign roles to each of the ants, like workers, soldiers, and drones. You got a little ant hill you can decorate and put different skins on. Starting April 8th, there's a new season called Race of Champions. Vast Jungle that you'll be able to sign up for. One of the coolest aspects of the game is that you can hatch different kinds of ants with different abilities based on real species with those characteristics alive today. Like the Gold Armor Ant, which you can get for free if you finish the 7 days login, the Reap Master, Slim Arched, or the Golden-Tailed Spiny Ant. The possibilities are endless. Right now they're celebrating their 3rd anniversary, so there's tons of new rewards to get in the game. They've also created a luxury gift pack for you, i.e. a viewer of this channel, to receive if you download the game. Just enter redemption code ANTS2024, and you will get 100 consecutive Supreme draws, and loads of resources to help you develop your ant kingdom. It's the best time to get powerful Reap Master or Slim Arched to guard your territory. Just download the game and log in now. Thank you, Ants Underground Kingdom, for sponsoring this video. Now, back to the time of their ancestors. So to understand why insects and other related groups got to godforsaken sizes during this period, we first have to check out what was going on with the flora that made their home all nice and cozy. Back in the Devonian period, the world saw the first large trees and forests that we know of. And now, in the Carboniferous, the plants are getting comfortable. They're taking shit over. The beginning of this period was real tropical, swampy. Plants were loving it, and they took on some forms that, based on fossil evidence, were absolutely sick. So, let me introduce you to a few of them. One of the most well-known and abundant trees during this time was Lepidodendron, also known as the scale trees. As far as we know, they could get to over 100 feet tall, with trunks that could get to 6 feet across. I came across some sources that said they could get to 180 feet tall, and then a couple other sources with 130 feet or somewhere in between that. So just know that's the range we're looking at across different sources. The scale trees loved swamps. They grew pretty densely all over them and were one of the biggest components of these swamp forests that we know of. They were made up of a single trunk that became branched at the top as an adult, with long, thin leaves that covered these branches and finished off with little cones at the very tips, like little Paleozoic ornaments. Absolutely sublime. Their trunk was covered in small diamond-shaped leaf scars, which were left all over them from shedding their leaves. And those scars, in some cases, became fossilized and eventually allowed us to identify them as fossils today, which is pretty insane. And like Wadiza and some of those earlier forms in the Devonian, scale trees used spores to reproduce rather than seeds, like ferns, fungi, and algae used today. Another tree from this time that's closely related to Lepidodendron is Sigillaria. Doesn't sound right, but that's apparently how you pronounce it. Sigillaria. They're both lycopods, and both had those diamond-shaped scars from fallen leaves. Sigillaria also got to over 100 feet tall as well. I would kill to see one of these in person, dude. I like this one a lot. If anyone knows how I can get my hands on a plant that looks like this, please let me know. I feel like there's got to be some sort of weird, fucked up succulent tree that kind of looks like this, you know? I feel like all those succulent trees kind of look like prehistoric trees. I love them. All right, moving on to a group of seed plants during this time. That's right, we've got some fucking seed plants during this time. Cordaites, a genus of trees and shrub-like plants with some members that could get to, you guessed it, over 100 feet tall that we know of. They had more leathery, strap-shaped leaves and were found in, you guessed it, swamps. It was Swamp City back in the day. But fossil evidence suggests they also tolerated a wider range of environments. The swamps, the mangroves, the floodplains, and also the upland forests. You name it. They were kind of up for everything, all over it. Some smaller specimens of Cordaites show evidence of aerial roots, which are exactly what they sound like. Roots exposed in the air, like the roots of mangrove trees. And the last one on the plant list is Colomites, a tall, hollow-stemmed plant, closely related to modern horsetails and kind of had a similar appearance, but much, much bigger. It had jointed hollow stems with needle-like leaves that came out of branches from the nodes on these stems, and seemed to have been able to reach heights of, you guessed it, 100 feet tall, that we know of, and lived in, you guessed it, swamp! I've definitely seen a succulent tree that looks like this one at the Oregon Zoo when I was there in November. They had all these little labels for all the plants they had on site, but they didn't have one for the one plant I wanted to get a name for, and I've been thinking about it ever since. It looked like this, and I don't know if it was a succulent. It kind of looked like if a pine tree was a succulent. I don't know if that makes sense. I'm way out of my comfort zone right now. But if anybody who has been to the Oregon Zoo knows what I'm talking about, please let me know, because I want one. Please tell me. Anyway, that was a very brief introduction to the plants that were alive during this time. The point is, plants were thriving. With a capital T. The world was absolutely lush, in a way it had never really seen before. So much so that their existence literally changed the concentrations of compounds in the atmosphere by a fuck ton, leading to those super high oxygen concentrations. So let me quickly break down why. I promise this is important before we get to the big insects. So, we all know photosynthesis. Plants take in sunlight, water, and carbon dioxide to make oxygen, which is released back into the atmosphere, and also sugar, which is stored in the plant and has all the carbon from the carbon dioxide. Gian, can you pull up a chemical equation of photosynthesis? So see, all the carbon from the carbon dioxide is in the sugar. 6 on one side, 6 on the other. This is like the only thing I got out of my chemistry classes in college. So all that carbon's sitting in the plants, and those plants are sitting in the swamp. When the plants died, they sat in these swampy conditions, which notoriously just don't allow materials to fully decompose. The whole thing with swamps. Also, fossil evidence suggests that the microbes that break down lignin, which is a key substance of these newly evolved plant structures, had not evolved yet. So lignin was just not being broken down. There was nothing to break it down. So these massive plants would sprout up really fast, pump a ton of oxygen into the atmosphere, pulling carbon dioxide out of it through photosynthesis, die, and then just pile up, meaning the carbon wasn't being released back into the atmosphere. So then, boom, oxygen concentrations were just fucking cruising on a highway to hell, about 30% compared to today's 21%. And this was sick for a lot of insects. It allowed them to grow to much larger sizes because of the way their respiratory systems work. Oxygen gets diffused directly into the tissues, so the increased oxygen made this efficient as fuck. This wasn't the only reason why some species got super big, but it was definitely a component for some. And also, not everything was giant. Actually, most things weren't giant. There were normal-sized ancestral grasshoppers and katydids, roaches, terrestrial scorpions that appeared for the first time in this period. There was a rapid diversification of flight, which, as of right now, now is kind of a jarring jump in the fossil record, like I talked about last time. Devonian fossils are like no flying insects, and then Carboniferous fossils are like, they fly now? A shit ton of different ways that these insects are flying, so that's just what the fossil record is right now. Evidence of metamorphosis appears here for the very first time, and also terrestrial snails, which aren't insects and not even arthropods, but wanted to mention that, didn't know where else to put that. But let's talk about the big guys. Often when people think of the Carboniferous, they think of those big dragonflies. That's what I think of. And the big trees. One of the most well-known dragonflies from this period is Miniminuteman, one of the largest flying insects to ever exist, that we know of. They had a 2.5-foot wingspan, which, to put in perspective, your bedroom door is probably 3 feet wide. They also have the same wingspan as a broad-winged hawk, and also a small gull. In other words, this was a big-ass dragonfly. Technically a griffinfly, which is morphologically slightly different. As we all know, nature doesn't give shit to you straight. Their larger size likely meant they had a wider variety to choose from on the Paleozoic menu. Lots of the smaller insects and other invertebrates, maybe possibly some amphibians as well. Fossils of their relatives, like other giant griffinflies, suggest they must have had to live in more open habitats rather than super dense forested areas, because their wings would have just fucking knocked into shit all the time. Or maybe they did live in a dense forest and they were just all sorts of fucked up when they were bopping around. Who's to say, really? Another one with a similar vibe to Meganura is Mesotheris enormis, named such because they were, you guessed it, enormous. There have only been partial remains from a single fossil found, but it displays enough evidence to say that they had a wingspan of nearly 2 feet long. They had unusually long cerci, which are paired appendages at the end of the abdomen of many insects. Some serve as sensory organs, others pinching organs, weapons, sex organs. Depends on what kind of freak the insect is. Not incest, though. That's cerci, not cerci. As for Mesotheros, the purpose of their cerci is unknown at this moment in time. All right, now, just so you know, we're moving away from the insects and into their relatives within the general terrestrial arthropod group. Fuck it. Let's do the arachnids first. Allow me to introduce you to Pulmonoscorpius, one of the largest scorpions to ever exist that we know of. The largest fossil remains so far represent an animal that could get to 2 feet and 4 inches long. You know what else is 2 feet and 4 inches long? A Canada lynx. This scorpion was about the size of a Canada lynx. I worked with a Canada lynx once, named Ramsey. He was rescued from a guy who tried to buy him as a pet, and Ramsey kept ruining his furniture and his condo, as a wild animal does. So Ramsey didn't like people very much, but he liked cardboard. He liked cardboard boxes. One time I made him a little cardboard box boat, called it the SS Ramsey. He really liked it. I bet he's sitting in a cardboard box right now. Anyway, sorry, that was a little break from the Canada lynx-sized scorpion that we're talking about right now. Unlike modern scorpions, which generally rely on mechanoreceptive senses for prey capture, Pulmonoscorpius seems to have relied on their eyesight much more. They had proportionally much bigger eyes than today's scorpions, which maybe makes them cuter. Like, they're kind of baby for that, but their size, dude, can't get past it. For a while, it was unclear whether they were just another sea scorpion, which we are all familiar with at this point, the Eurypterids. The Eurypterids are very different than regular scorpions. They actually shouldn't even be called sea scorpions because they're not the same thing, but there was confusion nonetheless. Turns out 2 specimens of Pulmonoscorpius show evidence of book lungs, which are air-breathing organs that land-dwelling arachnids tend to have. So boom. Terrestrial scorpion, arachnid, not a Eurypterid. I actually have an example that's the complete opposite of Pulmonoscorpius. That was originally thought to be an arachnid, but turns out is a Eurypterid. It's called Megarachnid, alive during this time. It was initially thought to be the largest spider to ever exist. Actually, people still mistake it as the largest spider to ever exist. It wasn't. It was 1.5 feet long, Eurypterid. The largest spider to ever exist that we know of is actually alive today, the Goliath bird eater, known to eat birds, largest by size and weight. They're about 1 foot long max. And up there with them, but a little bit lighter, is the classic godforsaken huntsman from, you guessed it, Australia.
What's he gonna do with him?
But enough about them, and on to our next arthropod on our lineup, Hibbertopterus, a sea scorpion, Eurypterid that looks like some sort of horseshoe crab, and also a strange shrimp. Kind of a funny looking guy. By the looks of them, you're probably thinking they were about the same size as a horseshoe crab, maybe a backpack-sized Eurypterid. Nope. Fossil evidence suggests the largest Hibbertopterus individuals could get to nearly 6 feet long. 6 feet long, dude. That's unnecessary for their shape, in my opinion. I don't mean to body shame them, but that just doesn't sit right with me. It's not scary, you know? It's just simply not right. It's like, I don't know about that. Their body shape with no context doesn't scream large to me, but maybe I'm just ignorant. Here's something that'll probably freak you out a bit. Hibbertopterus was a sea scorpion. Yes, a Eurypterid. But evidence of trackways that could only belong to them suggest that they spent at least some time on land. I don't like the idea of that body shape, of that size, walking around on land. You know? That just doesn't sit right. I'm sure you agree. This 6 feet long? On land? Yeah, no thanks. But the last one on our giant arthropods list kind of blows them out of the water on that front. It's probably the arthropod you've been waiting for, Arthropleura, a massive 8-foot-long arthropod that holds the record for the largest terrestrial invertebrate to ever exist. That we know. So here's the deal. Arthropleura is often considered a millipede. Makes sense, you know? The massive millipede, the biggest fucking millipede. I've probably said that, but they weren't technically millipedes, just millipede-like myriapods, which is the group millipedes belong to. So, millipede by association. Remember, the millipede form has been very successful. Don't you fucking forget. Do you remember Pneumodesmus numini, the earliest animal on land that we have direct fossil evidence of? Millipede form. In today's video, Arthropleura. And in modern times, we have millipedes that produce their own cyanide as a weapon. And millipedes in Australia actually have over 1,000 legs, because of course they would in Australia. Back to the millipede by association we're talking about today, the big one. How exactly they were able to get to this size is definitely due to a lot of factors. Diet being a big one. They likely needed lots of ultra-nutritious plant matter, and they might have even fed on other animals on land at the time, which wouldn't have necessarily been difficult for them considering they were some of the largest animals on the planet, walking the planet at the time. That we know of. Even bigger than many terrestrial tetrapods. Which brings us to the tetrapods. So last time in the Devonian, the vertebrates finally made it to land. It was the end of the no-bone zone. No-bone zone! And they did not waste any time getting established in the Carboniferous, along with being considered the age of the insects. The Carboniferous is also known as the age of the amphibians. So let's go over what they were up to now. Starting off with the temnospondyls, a group that was fucking all over the place. They're considered proto-amphibians, so not true amphibians, and maybe potentially the ancestors to modern amphibians. And they were very much taking advantage of the newly established land. Lots to see. Some species were smaller, like centimeters long, and the largest could get to almost 10 feet long. Some seem to live their lives almost fully, or sometimes you write something in the script that sounds like you'll be able to say it right when you talk it, but then you can't. Some seem to have lived their lives almost fully or fully in the water, while others seem to be fully down with the land. But all of them, as you would expect from proto-amphibians, still relied on water to lay their eggs in. Moving on to a specimen in a different category. The most well-known amphibian from the Carboniferous is Diplocaulus. Obviously, its boomerang head is a crowd pleaser. There are a few different species of a few different sizes, with the largest getting to about 3 feet long. They seem to have been more on the aquatic side of the amphibian spectrum, where they likely fed on small, aquatic creatures via ambush attacks. What exactly their boomerang head was used for is still uncertain. Lots of different ideas have been thrown out there, from defense, hydrodynamics, mating displays, or possibly somehow helping to funnel prey into their mouth. Exploring each of these possibilities is not really what I'm interested in at the moment though, because something else happened during the Carboniferous that would change the tetrapod course forever. What is a trait that the tetrapods we've gone over don't have that would have been necessary for the development of the lineage as we know it today? If you want to, pause the video. Try to take a second to guess what I'm about to say. You don't have to. Can't make you do anything. Actually, I'm gonna grab an example of what I'm talking about, so you gotta wait and think about it anyway. I'll be right back. I'm gonna be gone. An egg. Specifically, an amniotic egg. As you can see, this egg is very different than the eggs in the chia pudding that we talked about in the frog video, and also very different than fish eggs or other eggs in marine environments. This one's unfertilized because I got it from Trader Joe's, so it's really just for the visual aspect, but it will be useful nonetheless. So the classic fish egg or amphibian egg or any other egg is typically laid in water. They rely on the surrounding aquatic environment for the exchange of gases, nutrients, hydration, etc. The amniotic egg, on the other hand, has all that shit wrapped up inside of it. It has everything an embryo will need to develop. No need to be attached to a body of water. The shell does a decent job protecting the embryo from the elements, so they can be independent bitches. Bye-bye, ocean. I'm sure this is what the invention of the burrito felt like. Now I can take everything I want to eat and wrap it up in a protective shell and eat it wherever I want, go wherever I want with the burrito. No need for a fork, no need for a bowl. Got everything I need right here. And that's exactly what this amniotic egg allowed these newly evolved amniotes to do. Remember that during the Carboniferous, the global climate was going from wet and humid to cool and dry. Being able to lay your eggs away from a body of water opens up a huge variety of environments, a step that was definitely necessary for the survival of these tetrapods. On top of this adaptation, early amniotes also evolved water-resistant skin to prevent desiccation and diversified to shit. This was the root of the lineages that would lead to reptiles, birds, even mammals, who obviously would eventually keep the embryos inside the body. But we'll get to that in a few episodes. All right, just leave it right there. Okay. It might seem like the path to these lineages that we're so familiar with today seems like a ways off still, but that is not the case. Because not only did amniotes first evolve in the Carboniferous that we know of, they also seem to have their first major split here into synapsids and sauropsids. Synapsids were the ancestors to mammals, and sauropsids were the ancestors to reptiles. And the evidence of this is in the bones, specifically the skull. Let's start with the synapsids, our ancestors. Behind the orbit, or eye socket, of all synapsids is a single opening called the temporal fenestra. It's thought to have allowed for the expansion of jaw muscles and opened up the ability to process a variety of foods. And now all mammals today have a single temporal fenestra behind each orbit, with a couple exceptions, I'm sure, since nature never gives shit to you straight. But the whole synapsid lineage that led to mammals can be traced using this single pair of temporal fenestra behind the pair of eye sockets, which is fucking sick, in my opinion. One of the earliest synapsids that we know of is called Archaeothyris. It was about 20 inches long and had a sharp pair of enlarged canines, so most likely a carnivore. I know it kind of looks more like an ancestor to a lizard rather than a mammal, which is definitely due to that sprawling stance. That's like the OG trait for amniotes. This would eventually change to the legs underneath the body situation that we're more familiar with in mammals today. Another early synapsid from the Carboniferous, I think you're gonna like this one, is Adaphosaurus, a hefty fella. One of the oldest vertebrate terrestrial herbivores that we know of, and notable for the massive sail it had on its back, which might have been used as an early form of thermal regulation, maintaining the internal body temperature. That's what mammals do today, so that's pretty cool. Their form is probably a more familiar one to you if you've heard of their relative, Dimetrodon, came a little bit later. We're gonna cover them in the next period. I fucking love them. I love the sail. But throughout time, Hollywood has kind of misrepresented them to be a dinosaur. Classic Hollywood shenanigans. Nope. These were synapsids, in the group that gave rise to the mammals, including us, which is kind of nuts. This is in our distant lineage, rather than in the lineage with the dinosaurs. Okay, so what about the sauropsids? The ones that would give rise to the reptiles. What the fuck did they have going on? Well, like the synapsids, the key to the sauropsids was in the skull as well. The sauropsids had two different forms. The diapsids, which had two temporal fenestra behind the eye, and the anapsids, which had none. So, synapsids, one hole. Sauropsids, two holes, or no holes. The sauropsids have seen a shit ton of successful lineages. The dinosaurs, the pterosaurs, crocodilians, birds, I could go on. This is one hell of a group. So let me introduce you to some of its earliest representatives. First off, Hylonomus, one of the earliest anapsids that we know of. So they had no holes. They were about 8 inches long and kind of looks like lizards. They also had small, sharp teeth, which indicate a diet of insects that were abundant at this time. And next, Patrolochosaurus, considered the oldest diapsid that we know of. Another one that looked like a lizard, but this time with two holes behind the orbit. So we went over the age of the insects, got to the age of amphibians, and you might feel overwhelmed to find out that the Carboniferous is known as the age of another thing. Yeah, the sharks. The golden age of the sharks. Actually, more so shark relatives. This is the golden age of the wider group that includes sharks. One thing I've noticed science loves to do is be very generic when talking about what a shark is, like too generic, while simultaneously being very technical and being very exclusive of what a shark technically is. Let's do a little recap so you know what the fuck I'm talking about. So, back in the Silurian, the fish were going nuts. Chondrichthyes, the cartilaginous fish, first time popping up in existence, at least that we know of. Then they diversified into groups like acanthodians, the spiny sharks, which were not true sharks, but we still call sharks. And I forgot to tell you, in the last period, in the Devonian, a big shark thing happened, and I forgot to tell you. Two other major groups of chondrichthyans appeared for the first time in the fossil record. The holocephalans, also known as the ratfish, which have representatives today like chimeras and other ratfish. That's one. The other new group is the elasmobranchs, which includes sharks, skates, rays, sawfish, and their earliest representatives that we know of came from right about the middle of the Devonian. Phoebotus is the earliest elasmobranch, and Melanotus is the earliest holocephalan that we know of. Whoops. Sorry, I forgot about him last time. I know you bitches love sharks, so that's my bad. But anyway, now the Carboniferous is the golden age of the sharks. So allow me to introduce you to some of these golden age species, starting off with Dracopristis, an elasmobranch. It was first discovered in New Mexico in 2013 through an insanely well-preserved fossil specimen. It had a nearly complete skeleton, a body outline, and even soft tissue impressions, which painted quite the picture of what this species looked like hundreds of millions of years ago. Dracopristis was a nearly 7-foot-long shark, had 12 rows of teeth, sitting in extremely powerful jaws, and had a pair of spines on its back that were each over 2 feet long. They just so happened to look a bit reptilian, even though they obviously weren't, but definitely reminded the researchers of the reptilian form. So at the time of its discovery, they nicknamed it the Godzilla shark. They didn't know if it was a new species or if it belonged to a different species. Well, they figured it out. They were like, fuck it, looks like Godzilla. Let's call it Godzilla. And in 2021, it was finally identified as its own new species. and given the scientific name Dracopristis, which translates to dragon shark. So kind of the same vibe. It seems as though their large reptilian spines were used as defense against predators or other large sharks alive at the time. And despite their dragon or Godzilla-like appearance, they didn't seem to function as an apex predator based on their fossil characteristics. Their jaws suggest a lifestyle of not bottom feeding, but feeding on the bottom of lagoons, eating small vertebrates and crustaceans, like a chump. Alright, moving on to the holocephalans. You're gonna recognize the next two if you watch my video on the fucked up prehistoric sharks. This was the time of the fucked up prehistoric sharks. First up, Adestus. Not asbestos, Adestus. Also known as a scissor-tooth shark, due to the arrangement of their tooth whorls that kind of looks like a pair of godforsaken scissors, like Helicoprion's buzzsaw jaw. But two of them. By the way, Helicoprion technically did first appear in the Carboniferous, but it was their time to shine in the Permian, so gonna hold off on them until then. As you would probably guess, scientists initially speculated that Adestus used their scissor-tooth whorls like scissors, slicing prey right in half. But new studies with more advanced technology tell a different story. It's the same situation as Platybelodon's shovel map. Just because a part of an animal looks like a man-made object does not mean that it was used like that man-made object. No. Adestus seems to have used its tooth whorls to slash prey up and down, or snatch and slice, then pull the prey into its mouth using its lower jaw whorl. Regardless, it was heinous, and the size of their tooth whorls suggests that they could get to over 20 feet long, which is just woof. Alright, the next one is actually pretty cute. Stethecanthus, a smaller ratfish that could get to 2.5 feet long, and is known for the ironing board dorsal fin. The technical term for this ironing board dorsal fin is the spine brush complex. Brush, referring to a layer of placoid scales they had on the top of their dorsal fin and also on the top of their head, like a little toupee. The purpose of this complex? Uncertain, but the possibilities are deviant. And you know what? I'm gonna leave you on a cliffhanger. If you want to find out what those possibilities are, check out this video on fucked up prehistoric sharks, available on my channel, linked above and also in the description. Yep, you gotta engage with my content, sorry. I don't make the rules. And also because I want to introduce you to a couple little guys that I haven't introduced you to before. Like this one, Falcatus, another very small holocephalan that got to about 10 to 12 inches long. They also had a very strange dorsal situation, a little spine growing off the top of its head in the forwards direction. Scientists think this was likely some sort of display feature that possibly played a role in mating, and their big-ass, cute-ass eyes suggest they were adapted to deeper water hunting, maybe like my son. And another one, Iniopora, very cute, another holocephalan. That's all I have to say about them. So, nice. Don't think I forgot about the trilobites. But I don't have much news. In the Carboniferous, they were kind of starting to become less relevant. That's all there is to it. They were the extras in the feature film. Now let's move on to some more main characters. The strange specimens I know you've been waiting for. As we have already seen from the numerous species I've introduced you to from this period, things were just generally strange as fuck. So strange that they made up their own categories, rather than just another bullet point in the strange specimens list. So that means the ones I have left are just freaks. Absolute misfits. Let's start off with the most famous Carboniferous misfit, the one that was actually the topic of my first YouTube video ever, the Tully monster. Scientists don't know what it is. They don't even know vertebrate or invertebrate. Do you know how fucking weird you have to be, where scientists are absolutely stumped on whether or not you have a backbone? That is all sorts of fucked up weird. So let's talk about what they got going on. They had a trunk-like snout with a claw at the end. That's their mouth, and it had 2 rows of teeth inside of it. They also had eyes on stalks that extend sideways, a combination of traits not even remotely seen on any other animal, which has led to a decades-long debate on what the Tully monster is in the most generic sense, vertebrate or invertebrate. What is the Tully monster? The conversation started on the invertebrate side, as you would guess. None of the thousands of fossils found showed evidence of a backbone, and it stayed this way for a while. But then, in 2016, different research teams went off, using different kinds of technologies like synchrotron, elemental mapping, fucking lasers and shit. One team found evidence of a notochord, a vertebrate trait, and gills, another vertebrate trait, so maybe a jawless fish. Another team found melanosomes in the Tully's eyes, which is another vertebrate thing, so another point for the vertebrate. But another team suggested the eyes were simpler structures called cup eyes that are found in certain invertebrates. A few years later, there was a test on the zinc to copper ratio in the eyes, which suggested invertebrate. But then a team using lasers found keratin, which is a vertebrate thing. So long story short, nothing is settled.
That's all, folks.
The argument is still hot. Nobody knows what the fuck it is. The other misfit on this list kind of has the same situation, called Typhlosis, also known as the alien goldfish. They were very small, about 3.5 inches long. And like the Tully monster, Typhlosis could be a vertebrate. It could be an invertebrate. They had no fins, other than a little blade-like looking thing on their end, seemingly no backbone, no eyes, no shell, no anus.
What?
Yes, You heard me right. Only one hole for everything. This is nothing new in the animal kingdom. There are plenty of beings with only one opening. Jellyfish, notoriously, and other cnidarians like corals and sea anemones. Planarians, dude, look at a diagram of a planarian. Look at where their mouth is. Anyway, it sounds crazy, but it's not really crazy in the animal kingdom. So with all these qualities combined, scientists were like, what the fuck is this?
What are you?
And took a closer look in 2022. They saw what appeared to be some sort of toothy structure in the creature's fossilized gut, similar in appearance to the molluscan radula, which is like if you had a razor for a tongue that you shot out before your food even hit your mouth so that it's all cut up and shit. That's what a lot of mollusks are up to. Now, it might have been what Typhlosis was up to as well, maybe a mollusk, but there's a lot more research that has to be done. So I want to go back to what I talked about with the plants at the beginning of the video. Remember, the oxygen concentrations were so high because the amount of plant material that sucked up all the carbon dioxide, with very few ways for that carbon to decompose and get sent back into the atmosphere. This was not only significant for life alive at this time, but also huge for humans alive today because of what this plant material turned into over millions of years. To explain this more, I decided to bring on a really good friend of mine who knows more about coal than anyone else I know. The one and only Milo from Miniminuteman. There's a good chance you were introduced to me through my collaboration with him on his channel back in 2022, before I even started making long-form content. He got me in touch with his editor, Gian, who's down to help me get started and has been editing for me ever since. And so I owe my introduction to YouTube to him. I genuinely don't know where I'd be without his help and without Gian, because he does an unbelievable job bringing these videos to life. So I was stoked that I was able to track down Milo for this video. He's been traveling all over the world and just so happened to land in the perfect place at the perfect time for this collaboration. So without further ado, here is Miniminuteman.
Whoa, who's this guy? This doesn't look like Lindsay. Howdy, friends. My name's Milo Rossi. I am a science communicator here on YouTube specializing in archaeology. This is what I get for not charging my lav mic. The bird ambient noise is nice, the truck's compression braking aren't. And the reason I am in Lindsay's video today is because I am standing on top of the remains of these carboniferous swamps. Today I am in Tamaqua, Pennsylvania, located in the lower northeastern region of the state. And while I'm sure Lindsay is doing an incredible job telling you about the paleo environment of these unbelievable forests, I want to quickly whiz you about 330 million years into the future to tell you how these ancient forests played a very important role for everyone's favorite species of great ape. The immense, highly productive forests of the Carboniferous period would drop all of their natural debris on the ground, and year after year this would... Wow, they just don't let me talk about peat bogs anymore. And year after year, all of this natural material would build up to create a substance known as peat. Now, extrapolate that out for the hundreds of thousands of years that these forests existed, and you end up with some of the largest peat bogs that the world has ever seen. Time goes on, the Carboniferous forests come and go, but the peat bogs remain. They get covered by debris, continents collide with one another, and are ripped apart. And over hundreds of millions of years of geologic heat and pressure, the enormous peat bogs are transformed into the dense, black, highly flammable, carbon-rich material that we all know and love as coal. In fact, it is the coal deposits left behind by the Carboniferous coal forests that give the Carboniferous period its name.
Come a little bit closer, I'm all alone.
Yeah, okay, that's almost professional. We need to talk about coal. There are three different types of coal: lignite, subbituminous, and bituminous. Each type of coal being categorized by its carbon percentage, which dictates how well it burns. The lowest tier, the F-tier coal, is lignite. It's the least developed of the coals, only really a step away from peat, and has a carbon percentage between 25 and 35%. A little bit above that, we have the mid coal, which is the subbituminous coal. It's a little bit more developed than the lignite and has a carbon percentage of about 35 to 45%. And then above that, we have the most common type of coal, the A-tier coal, which is called, as you won't be surprised, bituminous coal. It burns hotter and longer than the other two with a carbon percentage between 45 and 85%. And both bituminous and subbituminous coal each made up 45% of the coal mined in the United States in 2022, making these two some of the most widely harvested and most common in the world. But I lied. There's actually not three types of coal. Because above these three very common ones, there is one type of coal that is incredibly rare but changed the face of our planet. It is a name that has become synonymous with the Industrial Revolution and is responsible for putting northeastern Pennsylvania on the map as a major manufacturing hub. That is, of course, anthracite coal. Ah, man, I'm actually kind of glad I'm using a shotgun mic because the train whistle in the back could not be more perfectly timed. The god-tier coal, known as anthracite, is between 85 and 97% pure carbon, and it is one of the most energy-rich raw materials we have ever discovered on our planet. However, it is incredibly rare, making up only 1% of the coal mined in the entirety of the United States of America. 100% of the anthracite coal mined in the United States in 2022 came from right here in northeastern Pennsylvania, being the largest and almost only anthracite coal field in the United States and one of the largest in the entire world. It's shiny, brittle, and can burn at temperatures exceeding 3,000 degrees Fahrenheit. So why is it that not all coal is created equal? What is the magic ingredient that turns bituminous coal into the god-tier anthracite coal? Well, just like pretty much every geologic process, it is a lucky combination of heat and pressure. If you look at this region of Pennsylvania from the air, you can see that the land almost looks folded. This is called the Valley and Ridge Province of the Appalachian Mountains. It is a series of anticlines and synclines, geologic terms for folds in the Earth's crust. Over time, the different stones that these folds are made out of have weathered, creating these unusual cross-sections of the enormous folds created by the collision of the African continent and the North American continent. This mountain-building event was known as the Alleghanian orogeny and occurred between 320 and 250 million years ago. This tectonic collision provided the necessary pressure to turn this peat into coal. But here in northeastern Pennsylvania, the pressure was just a little bit harder and had the added ingredient of the regions nearby carrying volcanic activity. This added an immense amount of heat welling up from the Earth's core into the mix of the already massive collision of continents. Because of this, the conditions on this part of the Earth's surface were just right to transform the colossal peat bogs from the Carboniferous forests into the dense, black, energy-rich anthracite coal. Now, the reason that I'm here in Tamaqua today is because Tamaqua is still home to an immense amount of coal mining. Coal was noted by colonizers in these mountains as early as the 1690s, but it wouldn't be until the early to mid-1800s that the resource was being fully exploited. And the anthracite coal from northeastern Pennsylvania literally changed the world. As the budding United States entered the Industrial Revolution, it was the coal from the very mountains that I sit on right now that fueled the fires. They powered factories, built railroads, and won the Civil War. The job opportunities that this massive deposit of anthracite coal created, both in mining and manufacturing, saw a massive influx of immigrants into the United States, including my ancestors who emigrated to the United States from Italy in the early 1900s. They, like many other immigrant families, worked in the anthracite coal mines, backbreaking labor done in pursuit of the American dream. The overgrown coal tailing pile behind me is a relic of this era, a time when northeastern Pennsylvania became the generator for the blossoming United States, allowing it to become the economic and industrial hub that powered it through the Industrial Revolution. Today, much of the anthracite coal in northeastern Pennsylvania has been vastly depleted, with events like the Knox mine disaster bringing an end to an era, with small pockets still mined, but humanity has begun to transition away from it as a resource in hopes of finding things that are more environmentally friendly and less destructive. But all of that is to say that we have one major thing to thank for our rise to a global superpower, and that is ancient primordial swamps that existed 330 million years ago. Well, that's all I have to say, and there's a pickup game starting over here. So thank you, Lindsay, for having me on. Again, my name is Milo Rossi. Feel free to check out my channel at Miniminuteman on YouTube, or you can type in Milo Rossi, you'll find me. Thanks again, Lindsay, and keep doing what you're doing. See you guys later.
So as you would probably guess from a process that was altering the environment to an atmospheric level, shit was not gonna end well. While this period didn't end with a major extinction, there was a minor one near the end of this time. It's called the Carboniferous Rainforest Collapse, and it happened about 305 million years ago. The gradual shift to cooler and drier climates meant that species had to adapt, otherwise they were gonna get booted. This might have been due to the higher oxygen concentrations kind of having a reverse greenhouse effect, but I'm gonna be honest, dude, the sources that I found for this collapse were kind of hard for me to get a good grasp on for some reason. Also, the formation of Pangea meant that all those coastal ecosystems at the merging points got squished out of existence, which I don't think is necessarily linked to the Carboniferous rainforest collapse, but that definitely happened and is worth mentioning. Long story short, the shift in climate led to the need for species to come equipped with new adaptations. But the end of the next period was going to be the biggest test of all time. If you like this video, be sure to subscribe so you don't miss my next video on a heinous deep sea creature. Right after, another quiz. Quiz 4. We got to quiz 4, so study for that. Get prepared for that. It's the last 10 videos. Check out my Patreon for behind-the-scenes updates and our Discord server. Download the Ants Underground Kingdom and use code ANTS2024 to receive a luxury gift pack to help you develop your ant kingdom. And a huge thanks to Milo for coming on for this video. And for now, stay curious. The world has a lot for us to learn. See ya! That's right, we've got some fucking plant seeds. Fuck, seed plants. Okay, let me do that again.